So hello Year 10 and welcome to lockdown learning again. And we're going to continue with the C8 topic, analytical chemistry or chemical analysis. And this is because we thought it made sense to finish this short topic and move on to a larger topic that will take us many weeks, rather than doing lots of bits as you had in lockdown 1, where you did a little bit of C10 and a little bit of C7. So we thought we'd get this done, get this finished, move on to another topic, and then come back so you'll have the opportunity, hopefully later in the year, to do some of the practicals from this topic. But we're going to get through the theory now. So this is technically lesson 5 in the series, and just to orient you, lesson 1 was all about formulations and pure substances. So what is a formulation? What's the difference between a formulation and just a standard mixture? Lesson 2 was all about RF values and look at chromatography in more depth. And we're going to come back for Miss Watt sets, and I'm going to film a video to show you the chromatography required practical and how that's carried out. And you may get a chance to do this later in the year. The third lesson is gas tests. Do you know your tests for chlorine, hydrogen, oxygen and carbon dioxide? And the fourth lesson is flame tests. Now, Miss Watt's classes haven't had the chance to do that, so I'm actually including that in this lesson here, flame tests. So for my set there's a little bit of a recap, but given that you did it the last lesson before Christmas, I'm not sure how much attention you were paying. Anyway, for Miss Watt's set all of this will be new. But the theme of today is testing for cations. So what is a cation? Well, when we try and identify what's in an ionic substance, we can do it by testing separately for the positive ions in the solution and the negative ions. A positive ion is called a cation. So in sodium chloride, the sodium plus ion is the cation. A negative ion is an anion, so the chloride ion is the anion here. Now, by the time we get to C4 and we're talking about anodes and cathodes and electrolysis, you do need to know these terms quite well. But for now, it's not essential. However, it's good if you start getting used to these descriptions. So how can you remember which is which? Well, the way that I remember it is I remember that cats, especially if you're stroking them and they're happy, they will purr. And cats are persitive. So cats are positive, cations are positive. In contrast, anions are like onions. Yes, they have layers, but also if you spend a lot of time around an onion, then you're going to start crying. They make you feel unhappy and crying and negative. So onions, just like anions, are negative species. So cations, cats purr, they're positive. Anions and onions are negative. So our first test, which is flame tests, is very much linked to fireworks. And when you've been out enjoying your fireworks display, I wonder whether you've ever questioned what gives fireworks their colours. Now, the more observant of you will have noticed that in the CH1 and CH2 classrooms, there's been a poster there, as long as I've been at the school, showing you different colours that are given out when different metals burn. So fireworks, actually, each one of these is a different metal burning. And different metals give out different colours. And we can use this to identify some metal ions. So this is the experiment. Flame test can be used to identify metal ions. You need to know about lithium, sodium, potassium, calcium and copper. There's just 5 of them, which give distinctive flame colours, and you need to know these flame colours, and you need to be able to identify species from the results of these tests, okay? Flame colours of other metal ions are not required knowledge, alright? So just these 5. How do we do it? Well, the method that we used was we had samples of different salt solutions, and we soaked splints, wooden splints, the sort that you would use to light your Bunsen. We soaked these splints in the salt solutions, and then we held them in the flame at the end. And we recorded our observations. Now, number 5 is really important. Ensure you record the initial colour, because after a few seconds the wood will start burning. This burns with a bright yellow flame. So once the wood starts to burn, you're going to have contamination in the colour you're looking at. So this is me and Mr. Reeves doing that experiment a couple of days ago. I hope it is informative. So here we are in the dark. A nice lesson just before Christmas. For those of you that had this, for those that didn't, well, hopefully this will make up for it. What we're doing here is we are testing for cations. That is the positive metal ions. And we can do that by first dissolving our chemicals into water, and then we can soak some splints into those solutions and hold them in a Bunsen flame. You may remember that this is the reason why the Bunsen burner was invented in the first place, so that Robert Bunsen could analyse the various colours produced to identify new elements. And the first one we're going to demonstrate is
lithium.
Lithium, so the flame colour of lithium. And hopefully you can see there a lovely red colour in the flame. A lovely red, we might even call that crimson. So that's one of the ones you definitely need to know. The lovely red colour of lithium. Now we've got
Sodium, next one there.
Sodium. Sodium gives us that very bright orange colour. You might recognise it from street lights. Now we've got to be careful here, because at some point the splint will start to burn, and at that point you will see the colour of the wood burning, which is a very bright yellow, the colour you would associate with things burning. So we must make sure that the colour we're observing is the colour before that takes place.
So we're now going down to potassium.
Potassium. Potassium is one of the hardest to see, but maybe you can see flashes there of the purple colour. We wouldn't describe it as purple. Your exam board wants you to call it lilac. So whenever we see a lilac flame, we know that it is potassium burning, and you would have encountered this before in the Group 1 metal reactivity series, where we demonstrated the reaction of potassium and water, and the potassium would have caught fire and would have burnt with a lilac flame. The fourth one here is
Calcium, sir.
calcium. And calcium there giving another orange flame, but actually a slightly different colour to the sodium. What I might ask Mr. Reeves to do is to take a splint from both the calcium and the sodium together and hold them in opposite sides of the Bunsen flame so that you can hopefully see the difference between the two colours. So the sodium is a lot brighter and is a lot more yellow. The calcium is a redder orange colour. The final one you need to know, there's two more. This one you don't need to know, but this is quite nice. This is strontium. So strontium giving another red flame, a slightly deeper red than the lithium, often described as a scarlet flame when compared to the crimson of lithium. Strontium often used in red fireworks. The final one you do need to know is copper, very distinctive. A lovely bright green flame here that you cannot mistake. And perhaps, since it's just after Christmas, shall we do copper and strontium together? The lovely red and green of Christmas. Thank you very much, Mr. Reeves. Okay, so as you saw there, and hopefully you are writing this down in your lab book, in your notebook as we go through. If not, please write this in your books. Lithium produces a crimson flame. You can say red, red's okay, but crimson is even better. Sodium produces a yellow or a yellow-orange flame. Not just orange, but yellow or yellow-orange. It's a very, very bright flame. You can't really miss that one. Potassium wasn't very clear on the video, particularly because the Bunsen flame was slightly purple anyway, but potassium produces a purple flame that you have to know is lilac. So you've got to be able to recognise that word and describe it as a lilac flame. Calcium, again an orange flame, but this time it is more red. So orange or orange red for calcium. Sometimes you'll see it called brick red. And copper, nice and easy. You saw it very clearly on the video, a green flame. As we can see here, things like rubidium, cesium, strontium, barium, titanium also give us flame colours, but you don't need to know those. You just need to know these 5 flame tests. So, just to recap, the flame test works on the fact that different metals produce different colours when put into a Bunsen burner. There is an alternative method that is sometimes described at GCSE. This is the method that's used at A-level, but don't be thrown if this method is used instead. The problem with the flame test, the problem with the test that we just saw is the fact that the wood starts to burn and you get some colour from that, which can mask the colour of the metal salt that you're identifying. So a better method is to use a nichrome wire. And this is used because it's unreactive and doesn't give a colour in a hot Bunsen flame. So the nichrome wire is dipped in hydrochloric acid and then heated to clean it. And this process is repeated until no colour is seen. So you keep putting it in hydrochloric acid, heating it, putting it in hydrochloric acid, heating it until you see no colour in the flame. You then dip the wire back into your hydrochloric acid, followed by your test sample. And this can be a solid, and this is the advantage of this. This is the second advantage of this. You can dip your wire straight into the solid test sample and put that back in the flame, and then you usually get a much cleaner flame than you do from the method with the wooden splint. So don't be thrown if people talk about sticking a nichrome wire into a flame. It's just like the splint method, only it's slightly more sophisticated. So here's a very simple example of using these ideas. You've got substance here. If you put this substance into a flame, you get a lilac colour. And if you heat it, it produces a gas which you can bubble through lime water, and the lime water goes cloudy. So what do we think is present? Here's a second sample. We put this into the flame and we get a green flame. We heat it, it gives off a gas that doesn't, when bubbled through lime water, doesn't make a change, but this gas will relight a glowing splint. So have a think, what could these salts be? Right, well, hopefully you identified the lilac flame as potassium and the green flame as copper. The lime water clearly indicates the presence of carbon dioxide. What sort of species release carbon dioxide? You should know this. You did this in year 7, you did this in year 9 with your substance X. A carbonate, CO3 2-, will release carbon dioxide. So you should be familiar with that from previous years. You probably identify this as oxygen. You're probably not entirely sure what's going to give off oxygen gas when heated. Well, not surprisingly, an oxide might give off oxygen gas. So our first substance we've tested separately contains potassium and carbonate. Our second substance contains copper and oxygen. So not surprisingly, the first one is potassium carbonate, the second one is copper oxide. It's a simple example, but this is the sort of thing you need to do in this topic. The second method you need to know of for testing for cations involves precipitation. And precipitation is when we get a solid formed from solution in a reaction. So two solutions forming a solid when they react together. And this is quite a complicated table here, but essentially soluble things are yellow, insoluble things are orange, and we can see here that hydroxides tend to be insoluble. Moreover, hydroxides have a range of interesting colours, and we can see that here. We've got blues, we've got greens, we've got pinky purples, we've got light browns, dark browns, whites, browns, that's even a dark green. So how can we use this fact to help us identify cations that are present in an unknown sample? Well, what we can do is we can react our unknown with a metal salt solution, we can see if a precipitate is formed, and if a precipitate is formed, the colour of the precipitate may be able to tell us what was the ion that was there initially. So as it says here, if we add sodium hydroxide to a metal salt solution, then a precipitate may form. And this can be used to identify the cation by its colour. So, here is the experiment. You need to know 6 different ions and what happens when sodium hydroxide is added. And again, you need to write this down in your books. So the first thing we're going to do is we're going to add a small amount of sodium hydroxide, and then we might go on and whack in a bit more sodium hydroxide and see what happens to each of these. So we've got an aluminium solution, a copper solution, an iron 2 solution, an iron 3 solution, a magnesium solution, and a calcium solution. And here's the method. Core to fill a test tube with initially your aluminium salt solution. It's aluminium sulfate. We're then going to add a few drops, and that is important that we start off with just a few drops of sodium hydroxide solution. Note your observations, that's in the second column. Repeat with solutions of copper, iron 2, iron 3, magnesium and calcium. If the solutions produce a white precipitate, and only if they produce a white precipitate, then add more sodium hydroxide until the test tube is a half full. If you want to speed this up, you can shake the tube at this point. You don't have to, but it speeds up the reactions. And note if anything else happens. So, here's myself and Mr. Reeve doing this experiment a couple of days ago. Enjoy. So, this is the second video showing you the tests for cations, that is the positive metal ions that you find in salt solutions. And in this experiment we're going to be looking at the tests for aluminium, calcium, copper 2, iron 2, iron 3 and magnesium ions. And each of these solutions has been put into a test tube, and Mr. Reeves is going to add a few drops initially, and that is really important, a few drops of sodium hydroxide. So first to the aluminium sulfate solution on the left. Well, we can see there definitely a precipitate being formed there, a white precipitate forming in the aluminium solution. Now sodium hydroxide being added to calcium chloride, and again we can see a white precipitate being formed. Copper sulfate, copper 2 sulfate I should say, and the copper solution is reacting with the hydroxide to form a pale blue precipitate. Now iron 2. Now that is an unexpected colour there, not for me, but for you guys, a dark green, almost black colour being produced when hydroxide reacts with iron 2. Now for an iron 3 solution. A few more drops there, please, Mr. Reeves. And we can see a brown precipitate being formed when hydroxide reacts with the iron 3 solution, and finally magnesium on the right. And we can see a white precipitate being formed there. So the copper is easy to identify, pale blue precipitate, iron 2, dark green precipitate, and iron 3 as the brown precipitate. But between the aluminium, the calcium and the magnesium, they are all forming white precipitates. So we need to be able to distinguish between those three. One of these three solutions can be identified via a flame test, as you've seen previously, so have a think about which one that is. However, there is another test we can do to check for, to distinguish between these three white precipitates. What Mr. Reeves is now going to do is put a whole squirt of sodium hydroxide into each of these tubes. First, aluminium. Now, what is happening there, which is quite surprising, is when we added the hydroxide, it initially formed a white precipitate, but as we add more hydroxide, that precipitate is actually starting to redissolve. And we can see the precipitate there has disappeared, or almost disappeared entirely. Let's try the other thing. Let's try the same thing with calcium chloride and magnesium sulfate. So first adding what we call an excess of sodium hydroxide. Giving that a quick shake. And the same thing with the magnesium sulfate on the right. And Mr. Reeves is going to give that a quick shake. Excellent. So there, the aluminium sulfate initially formed a white precipitate with a small amount of sodium hydroxide, about 5 drops, but that precipitate redissolved in excess sodium hydroxide, while the calcium and magnesium solutions did not redissolve in excess hydroxide. So as you saw there, the copper solution formed a light blue precipitate, and that was easily identifiable. We didn't need to do the second test. An iron 2 plus ion forms a dark green, almost black precipitate. Again, very easily identifiable. We didn't need to do a further experiment. Iron 3 plus forming a brown precipitate. Looked a bit like rust. That's because it is basically rust, and we didn't need to do a further experiment. But aluminium, magnesium and calcium all produced a white precipitate. There were some subtle differences between the precipitates, but it was not easy to identify which was which was which. And if you were just handed a solution you didn't know, how could you identify which one's aluminium, which one's magnesium, and which one's calcium? Well, this is where the second test came in. Because when we added a lot of hydroxide, so excess sodium hydroxide, what we saw is that the aluminium redissolved. The other two did not. There was no change. So this allowed us to distinguish between aluminium ions and magnesium and calcium ions. This is also why you need to be careful and only add a small squirt of hydroxide in the first case, because if you add too much, you're going to miss that fact that aluminium initially forms a precipitate, which then redissolves. So do be careful when you're doing that. Now, we're going to introduce at this point something called an ionic equation. And the ionic equations are something that if you do chemistry at A level, you really do need to be able to do. And a lot of students manage to go through their GCSEs without ever really understanding ionic equations. But they do come up quite regularly. And we're going to start simply. So, in that experiment, when we added sodium hydroxide to copper sulfate solution, hopefully you could have worked out that if we react copper sulfate and sodium hydroxide, well, they just swap partners, so the sodium ends up with the sulfate and the copper ends up with the hydroxide. So they just swap the anions and the cations around to form the opposite products. And here is the chemical equation: CuSO4 plus NaOH, sodium hydroxide, CuOH2, copper hydroxide, sodium sulfate. You should, from C2, be happy with ionic compounds and formulae. If not, you may need to go back and recap some of the ideas from that. The first thing you need to do is balance this. Well, we've got one copper on the left, one copper on the right, that's fine. We've got two hydroxide ions there, so we need two hydroxide ions on the left, so we must have two sodium hydroxides. If we've got two sodiums there, we've got two sodiums there, that balances. We've got one sulfate on the left, one sulfate on the right, excellent. Now notice that I kept the hydroxide together and the sulfate together when doing that balancing, and that is something that you will probably want to get used to, that these special groups that we introduced you to in year 9 behave as a single atom. So yes, we could have balanced the sulfurs and the oxygens separately, but if you start balancing the oxygens and say, oh well, there's 5 oxygens on the left and there's 5, 6 on the right, you're going to get into trouble. It's much easier to just balance these complicated groups together. Having balanced the chemical equation, the next important thing is that you need to be able to write the state symbols. Now we know we started off with copper sulfate solution, so that must be aqueous. We know that sodium hydroxide is an alkali, it is a solution, so that is aqueous. We said earlier, didn't we, it is the hydroxides that are typically insoluble, so it should come as no surprise that the insoluble precipitate, the solid, is the copper hydroxide, the sodium sulfate is soluble. To write the ionic equation, we just have to say which ions combine to form the insoluble product. So if the insoluble product is copper hydroxide, what ions are in that? Well, as long as you are paying some attention, and you have been paying attention through the chemistry course, you should realise that a hydroxide ion is OH minus, and there are 2 of those, and therefore they must be balanced by a Cu2 plus ion. So in that copper hydroxide there are 2 hydroxide ions and a copper ion. So therefore, one copper ion that is soluble, state symbols are really important here, so a soluble copper ion reacts with 2 soluble hydroxide ions to form copper hydroxide. If you didn't remember the charge on hydroxide, you could work it out. You know that sodium up here, sodium, NaOH, sodium is always 1 plus because it's a group 1 metal. So therefore the hydroxide must be OH minus so that the charges are balanced in NaOH. Once you know that, again, you know that the copper must be 2 plus to balance the charges with the 2 hydroxides. The idea here is really simple, provided you've been following the chemistry so far. So as long as you know ionic substances, you know how the ions are put together from C2, literally all you're doing here is you're taking the product and you're working out the ions that were in it. As I've said many times, if you are not learning the basics, there's a huge amount of work in writing these ionic equations because you don't have a clue what the charges on these things are, and you may not even know how to work out those charges. So here's an example for you to have a go at. Adding sodium hydroxide to iron 2 sulfate. Again, we've got the reaction is iron 2 sulfate and sodium hydroxide. They swap partners to form iron 2 hydroxide and sodium sulfate. And here is the unbalanced equation. FeSO4 plus NaOH goes to FeOH2 plus Na2SO4. So step 1, you need to balance it. Step 2, you need to add state symbols. And then step 3, the new bit, can you write the ionic equation for this reaction, showing which ions combine to form the insoluble product? Now I've given you some help here. I've reminded you that hydroxide is OH minus, and I have also reminded you that because it's iron 2 sulfate, the iron must be Fe2 plus. But pause the video, have a go. Right, balanced chemical equation. We've got one iron, that's already balanced. We've got 2 hydroxides, so we need 2 hydroxides here, 2 NaOH. 2 sodiums here, 2 sodiums here, that balances. 1 sulfate here, 1 sulfate here. That's all good. So the balanced chemical equation is fairly straightforward. Which is the insoluble bit? Well, hopefully you have cottoned on now. It is the hydroxide product that is insoluble. So adding the state symbols, iron sulfate was a solution, it's soluble. Sodium hydroxide is soluble. As we said on the previous slide, sodium sulfate is soluble, iron hydroxide is not. So in order to work out what the final ionic equation is, you just need to be able to tell me what ions are in iron hydroxide. Well, the iron is Fe2 plus, and there are 2 OH minus ions. So the overall equation, the ionic equation, Fe2 plus aqueous plus 2 OH minus aqueous, forming CuOH2 solid. Do make sure you are copying these examples down in your books with sufficient detail that when we come back to ionic equations in C4, you have an idea of what you're doing here. Okay, here's a third example. We didn't use calcium sulfate in this experiment because calcium sulfate is insoluble, and in order to do these precipitation reactions we need a solution. Therefore we demonstrated with calcium chloride, so your reaction is going to be slightly different, but the same principles apply. Calcium chloride and sodium hydroxide make calcium hydroxide and sodium chloride. They swap partners. And here is the unbalanced equation. So again, number 1, balance the equation. Number 2, add state symbols. Number 3, what's the ionic equation? I have reminded you that calcium is group 2, so it is Ca2+. Pause the video, have a go. Right, balancing this equation, 1 calcium, fine. 2 chlorides, 1 chloride, so it must be 2 NaCl. 2 hydroxides means we must have 2 NaOH. So checking the sodiums, we've got 2 sodiums on the left, 2 sodiums on the right, so our balanced chemical equation is that. Which product is insoluble? Well, by now, you instantly should recognise that the insoluble product is the calcium hydroxide, so adding those state symbols is second nature. Which ions combine to form the insoluble product? Well, in calcium hydroxide here, what do we have? Well, we know that calcium is Ca2+, and we must have 2 OH minus ions, so therefore a calcium ion in solution and 2 hydroxide ions in solution combine to form calcium hydroxide solid. Okay. The final example, and this is the hardest, when you add sodium hydroxide to aluminium sulfate, back to sulfates, aluminium sulfate is soluble, the reaction is as follows. 1, can you balance it? 2, what's the insoluble product? 3, what's the ionic equation? I've reminded you down here that aluminium is 3+ because it is a group 3 metal. Pause the video, have a go. Right, balancing this was slightly more difficult, but if you started with the aluminium, it was quite straightforward. 2 aluminiums here mean 2 aluminium hydroxides over there. 2 aluminium hydroxides over there mean that there are 6 hydroxides in total. 3 in each AlOH3, and there's 2 of those. There's 6 hydroxides, which means we must have 6 NaOHs. If we have 6 NaOHs, we have 6 sodiums. There's 2 in sodium sulfate, so that means we must have 3 sodium sulfates, so there are 6 sodiums. And just checking, we have 3 sulfates on the left, we have 3 sulfates on the right. Everything is now balanced, and well done to you if you got that right. What are the state symbols? Again, I mean, this is not difficult by now, is it? The hydroxide is insoluble. What's in that aluminium hydroxide? Well, actually you've got aluminium 3+ ions, and you've got 3 OH- ions in that chemical. So the overall reaction here is either that 1 aluminium and 3 hydroxide ions forms 1 AlOH3 particle, or, as I've written down here, you may have said 2 aluminium ions and 6 hydroxides formed 2 aluminium hydroxide particles. Either one of those is fine. Right, back to the easier stuff. This is how we tested for it. We added a small amount of sodium hydroxide, blue precipitate copper 2, green precipitate iron 2, gelatinous brown precipitate iron 3, and these come from the transition metals. Okay, so these coloured precipitates come from transition metals, and again you should be familiar with that from C1. So back in C1 you looked at the difference between S block metals and transition metals, and you saw that coloured compounds come from transition metals. The reason we can't use this to test for group 1 hydroxides is that group 1 hydroxides are soluble, so it can't identify lithium, sodium, potassium. However, we can use a flame test for that. Group 2 and 3 metals form white precipitates. And the 3 you need to know here are, in no particular order, that aluminium, calcium and magnesium give you a white precipitate. How can we identify them? To remind you that aluminium hydroxide will redissolve in excess sodium hydroxide, the others won't, and we can identify calcium by using a flame test. Aluminium and magnesium do not give distinctive colours in a flame test. So, if a solution forms a white precipitate, the precipitate doesn't redissolve, and it doesn't give an interesting colour in a flame test, what is the cation? I'm going to leave that for you to think. And here is the flow chart for this. You take your unknown solution, you add sodium hydroxide. If the precipitate is coloured, it must be copper iron or iron. If it's reddish brown, it's iron 3. If it's blue, it's copper 2. If it's light green, it's iron 2+. If it gives you a white precipitate, is one of these 3. Now, other ions do give white precipitates. Alright? So don't think, just because something gives a white precipitate, it has to be one of these 3, but these are the 3 that you need to know. So if you add excess sodium hydroxide and it gives you, it redissolves, then it must be aluminium. If it's insoluble, it's got to be magnesium or calcium. How can you tell the difference? You stick it in a flame test, and calcium will give an orange-red flame test. Magnesium will give no colour. Right, well, hopefully that was useful. You may or may not have questions to do depending on whether this is the first or the second lesson of the week that you tackle. But anyway, in next lesson, we're going to go through and we're going to looking at the anions and how can you tell what are the negative ions in an ionic substance. Thank you.